Section 8 is relative motion. So we have in this first example, Amy, Bill, and Carlos each measure the velocity of the runner. Okay? So Amy's just standing there, Bill is on a bike, and Carlos is in the car. The velocities are shown relative to Amy. Okay, so Amy's just standing there. She sees the runner going at 5 meters per second. She sees Bill going at 5 meters per second on the bike. She sees Carlos going at 15 meters per second in the car. Okay? Now, the question though is, how does Bill see the runner moving? At what speed does Bill see the runner moving? And the answer is, relative to Bill, the runner is not moving. Okay? Because Bill and the runner have the same speed. They have the same velocity. They're going in the same direction at 5 meters per second. So, really, Bill sees the runner moving his legs up and down, but the runner isn't going anywhere relative to Bill. Okay, so relative to Bill, the runner's velocity is 0 meters per second. Okay. What about relative to Carlos? How fast is the runner going? Well, Carlos is moving forward in the positive direction at 15 meters per second. The runner is moving in the positive direction as well, but only at 5 meters per second. So Carlos is like speeding away from the runner at a difference of 10 meters per second, which is relative to Carlos, making the runner go away from Carlos at a speed of 10 meters per second in the negative direction. Okay, so that would mean, according to Carlos, that the runner has a velocity of negative 10 meters per second. Okay, so that's what relative motion is all about. According to Amy, you're looking at the velocities of these people. According to Bill, the runner has a velocity of 0 meters per second. According to Carlos, the runner has a velocity of negative 10 meters per second. Okay? So, relative motion is getting at this idea that in reality, we can't really say what anybody's velocity is ever, because it's all defined based on where you set up and what you are doing. Okay? If you are stationary and you're set up in a particular location, then you have velocities defined based on your location and your velocity. Okay? So everything is relative to you. So that's what we're going to be talking about in this section. It's a little bit tricky to wrap your head around, especially the first time that you start thinking about relative motion. But if you've ever done like little thought experiments on this before, then probably you're going to be at an advantage as we go through this section. So here we go. So there is no single true velocity for an object. We can define an object's velocity only relative to the observer who is measuring it. Okay, that is the single most important concept of this section. So we have, in this example, researchers doing satellite tracking of albatrosses, so the gigantic bird, in the Southern Ocean, observed a bird maintaining sustained flight speeds of 35 meters per second, which it says is nearly 80 miles per hour, which is extremely fast for a huge bird. So it seems surprisingly fast until you realize that this particular bird was flying with the wind, which was moving at 23 meters per second. All right. So what's the bird's airspeed, which is its speed relative to the air? This is the truer measure of its flight speed. Okay. So we clocked it. We're sitting there on the ground and we see it fly by at nearly 80 miles per hour. Okay. That's relative to us on the ground. But the question is, relative to the air that it's in, how fast is this bird moving? Okay, so Obviously, it's going to be a little bit different if the air itself is moving at 23 meters per second. Okay, so we got to figure out a way to develop. We have to develop some notation and then figure out a way to make the distinction between the two things. So let's get into it. So the first thing that would be helpful would be probably to draw a picture. Okay, so we have. I'm going to draw a really awful picture of a bird, and it's already bad. So just here's our bird. Okay, it's actually turned out okay. Here's the bird. Okay, the bird is flying in this direction, and then we have the wind behind it. Okay, the wind behind it is helping it move faster. So the velocity of the bird, okay, relative to, so it says the uh, bird maintained this speed, okay, and it was flying over the ocean, so it's flying over the water. So the velocity of the bird relative to the water, okay, that's how we want to note that. So we have velocity sub bw, the velocity of the bird relative to the water here. And then behind it, all of these little arrows that I drew is sort of, I'm trying to represent the wind, okay, the wind behind it. Really, I only needed one arrow there, but I'm just trying to represent the wind. So now this is going to be the velocity of the air, okay? The velocity of the air. I don't want to use the velocity of the wind because that's going to be a W. The velocity of the air, again, relative to the water, okay? And we're all moving to the right here. So the velocity of the air relative to the water, the velocity of the bird relative to the water. It's all relative to the water. The water is not moving, okay? Now, what do we know? Well, from the problem, everything's in the x direction here. So we know that the velocity of the bird relative to the water, we measured it to be this, 35 meters per second. And we know that the wind was moving at 23 meters per second. So that is the velocity of the air relative to the water. It was 23 meters per second. What is it we're looking for? Okay, it says the bird's airspeed. In other words, its speed relative to the air. So we are looking for the velocity of the bird, okay, velocity of the bird relative to the air. That's what we're looking for. Okay, that's what we want to know. So, how do we do this mathematically? What we do is we say the velocity. Okay, this type of equation is going to be set up pretty much like this all the time. So the velocity of the bird relative to the water is equal to the velocity of the bird relative to the air plus the velocity of the air relative to the water. And the reason that I'm setting it up like this is if you look at this notation, we have velocity of the bird relative to the water here, okay? And notice that I have bird and water here. And then the inside notations are air and air. It's kind of like when we're doing matrices in Algebra 2, we need the inside notations to match. Kind of like the same thing is going on here, okay? So the velocity of the bird relative to the water is equal to the velocity of the bird relative to the air plus the velocity of the air relative to the water, okay? So then when we add those together, those inside dimensions almost are needing to be there so that we wind up adding them out and we wind up with the velocity of the bird relative to the water. That's pretty much what's happening, okay? Now, we don't want velocity of the bird relative to the water. We want the velocity of the bird relative to the air. So we're actually going to solve this equation for the velocity of the bird relative to the air. And we'll do that by subtracting the velocity of the air relative to the water from both sides. So now I have V sub BA equals V sub BW minus V sub AW. And now I can just substitute those things in. I have V sub BW is 35 meters per second minus V sub AW is 23 meters per second. So that means the velocity of the bird relative to the air, which is what we're looking for, is equal to just 12 meters per second. So in reality, the bird relative to the air was only flying at 12 meters per second, but because the tailwind was so strong, it was actually able to move relative to the ground at nearly 80 miles per hour. Okay, so that's what a tailwind will do for you. So that's how you do a problem like that. Okay, they're all set up very, very similarly every time, just like this. So this equation that I have sitting right here can be tailored to whatever problem it is that you're doing. Just think about what the notations need to be because they'll be different every time, but it's the same, very, very similar looking setup. Okay, so let's take a look at this one. Cleveland is approximately 300 miles east of Chicago. Okay, so let's start drawing a picture. We have a city here and a city here. Cleveland is approximately 300 miles east of Chicago. So this would be Chicago, and then Cleveland here. A plane leaves Chicago flying due east at 500 miles per hour. The pilot forgot to check the weather and doesn't know that the wind is blowing to the south at 100 miles per hour. What's the plane's velocity relative to the ground? Okay, so we have, we want to be flying this way, directly to Cleveland. Okay, due east at 500 miles per hour is our intention. But there is a wind blowing to the south at 100 miles per hour. So the wind at 100 miles per hour is blowing us this way. And the plane then, the resulting direction of the plane is going to be like that. So we've just created a nice right triangle sitting here. Okay? What's the plane's velocity relative to the ground? What has happened is we've basically created component vectors. We have 500 miles per hour east, 100 miles per hour south. So we have created component vectors here, and we just need to find the hypotenuse and the angle that is created. So let's think about how we're going to do that. Okay, we know that this velocity here, the velocity of the plane, the intended path of the plane, right, is 500 miles per hour. Okay, in that direction. But the wind is blowing at 100 miles per hour south. So right triangle, directly opposite this one is the hypotenuse. So Pythagorean theorem will get us there. Our velocity, our actual velocity, is going to be, so velocity equals the square root of 500 squared plus 100 squared. And so therefore our velocity is equal to, if we do that math, with significant figures, we get 510 miles per hour. Okay, but that's not it. That's just the speed. We need the angle here as well. So to do that, we know this side and we know this side. Those are both the sides of a triangle, not the hypotenuse. So that would be opposite and adjacent. That's tangent. So tangent of our angle theta equals opposite over adjacent. The double zeros on the top and the bottom are gone. and I need to take the inverse tangent of both sides. So theta equals arctangent of 1/5. Okay, we need to be in degrees. We enter that into our calculator, and we wind up with theta equals just about 11 degrees. So now we need to formulate an answer. That is an 11-degree angle, but we need to state that this is 510 miles per hour, and that angle is 11 degrees. 11 degrees, and we were going east, but we wound up going south of that. So south of east. That is our answer. All right. By the way, the pilot forgot to check. Not good. Not a good pilot. Okay. The water in a river flows downstream at 3.0 meters per second. A boat is motoring upstream against the flow at 5 meters per second relative to the water. Relative to the water, that's important. What is the boat's speed relative to the riverbank? Think about it. We could draw a picture for this one, and it would be might actually make this a little bit easier. Um, Downstream is, let's just call that down, right? Upstream is up. Let's do that. That makes upstream positive. So upstream is positive, and downstream is negative. Okay. So water in a river flows downstream at 3 meters per second. So that would be this way, -3. And then the boat is motoring upstream against the flow at 5 meters per second relative to the water. So this way at 5 meters per second. Okay. Relative to the water. So what is the boat speed relative to the riverbank? Well, relative to the water, it's moving at 5 meters per second. Okay. So if I'm sitting in the boat, my speedometer in the boat says 5 meters per second, right? But the water itself is moving at 3 meters per second the other way. So even though my speedometer says 5 meters per second, that's relative to the water that's moving at 3 meters per second the other way. So that means somebody on the riverbank is looking at me and watching me go 2 meters per second. The answer is D. Hopefully that makes sense. It's all relative to the fact that I'm on a boat on water that's moving at 3 meters per second downstream. Okay. That is it. We're done with the section, and that was the last section of the chapter. So all of the odds now for the chapter can be done.